Tree lines, especially alpine tree lines, are one of the most fundamental borders in nature, indicating a transition from the globally important life form, tree, to non-forested systems. Large-scale tree-line patterns have been a focus in ecology and biogeography for centuries. Alexander von Humboldt noticed already in the early 19th century that tree lines increased towards the equator. In the mid-20th century, first global assessments of the tree-line elevation-latitude relationship were made by Karl Troll and Karl Hermes. Around the turn of the century, Christian Kerner and colleagues identified that thermal constraints govern tree-line formation by using in situ climate measurements. To start out, let's define what a tree line is.
Like in most cases in nature, abrupt borders generally don't exist. Rather, transition zones, so-called ecotones, characterize changes in nature. This is the case for tree lines too. Two aspects of the treeline ecotone are particularly interesting. A, the actual tree line, that is the upper limit of the growth form tree, and B, the tree species line, indicating the uppermost limit of individuals of the tree line forming species. The tree species line can lie many meters above the tree line, but tree species often only show stunted or shrubby growth. In the following study, we will be focusing on the tree line only.
However, traditionally, tree-line science has focused on mainland mountain systems, while islands have been neglected in this respect. Interestingly, island tree lines might behave differently than mainland tree lines due to island-specific features such as isolation, endemism, geologic origin, or young age. A new study by Severin Irrel and his colleagues, recently published in Ecography, aims at filling this research gap by asking the following questions.
We wanted to know if island tree lines are lower than on the mainland. This has been postulated in the past, but a global analysis confirming this difference is still missing. In the next step, we asked, how does the geological origin of an island influence treeline elevation? Islands can generally be separated into two main types: continental islands, which are often of complex geologic origin and have had contact to the mainland throughout their geological history, and oceanic islands, which are of pure volcanic origin and have been permanently isolated from the mainland. We assumed that oceanic islands would have the lowest tree lines due to their isolation and smaller size, whereas continental islands would take an intermediate position as a result of their relative similarity to the mainland. In the final step, we were interested in how local island characteristics affect island treeline elevation on the global scale. We assumed latitude as the main thermal driver on the global scale to be most important, but also tested different island biogeographic variables such as maximum island elevation, area, isolation, and species richness, which represent important features of islands.
Irrel and colleagues have compiled the largest data set for island tree lines up to date, altogether recording 86 island tree line elevations ranging from 70 degrees north to 56 degrees south. To achieve this, they used easy-to-handle and ready-to-use satellite imagery combined with a digital elevation model, namely Google Earth.
We did a systematic sampling of all oceans searching for island tree lines. Where the resolution of the image permitted it, we sampled the highest tree line of each island. We were surprised how well it worked and how simple a method it was. In the example, we can see individual trees at the tree line of La Palma Canary Islands. The following clip shows that the tree line is quite distinct and individual trees are clearly visible at the tree line. Then, in the next step, we collected island-specific data such as maximum island elevation, species richness, or area from different island databases for further statistical analysis. Our results show, if corrected for latitude, that treeline elevation significantly decreases from the mainland through continental islands to oceanic islands. This likely has to do with the fact that oceanic islands have smaller areas, lower maximum elevation, lower plant species richness, and highest isolation, while continental islands take an intermediate position in this respect. Using general additive models, or GAMs, we clearly identify the double-hump treeline elevation-latitude relationship for the mainland, with a maximum in the subtropics of both hemispheres, while both continental and oceanic islands show a single peak in the tropics. Large mountain chains in the interior of continents, such as the Himalayas or the Andes, produce subtropical peaks on the mainland. However, such large land masses are lacking on subtropical islands. Rather, high aridity as a result of the frequent trade wind inversion is responsible for subtropical island treelines, likely lowering them below the actual thermal treeline. To our surprise, maximum island elevation and not as expected latitude was the single most important predictor for treeline elevation on islands. We interpret this as evidence for a strong mass elevation effect. The mass elevation effect has been predominantly ascribed to large continental mountain ranges, but our results clearly suggest that this effect, which ameliorates the microclimate providing better growth conditions for trees, is already present on relatively small landmasses such as islands.
To sum this up, Errol and colleagues comprehensively study island tree lines for the first time using a promising method based on ready-to-use satellite imagery. Applying simple island biogeographic variables, they are able to explain a very large fraction of the variance, thus adding to our general understanding of global tree line formation. The simple quantification of the mass elevation effect might be a useful tool for treeline studies beyond islands, possibly spurring further studies in this direction.